Welcome back to the MVPN video series. In today's video, we introduce the topic of Multipoint Label Distribution Protocol, or MLDP, and we discuss how it goes about creating multipoint label switch paths, or simply MPLSPs. So let's begin. Now, at a very rudimentary level, MPLSPs are tunnels with multiple endpoints. So just like a point-to-point LSP, aka an LSP, has two endpoints, an ingress endpoint and an egress endpoint, a multi-point LSP has multiple endpoints. Now, depending on its behavior, an MPLSP can further be of two types. If you look at the LSP on the left-hand side, it has a single ingress LSR and multiple egress LSRs. In this case, it is called a point-to-multipoint LSP. To visualize this as a traditional multicast tree, think of an S, G tree with a single source. Within the scope of this series, we've already seen this. We've seen this as data MDTs. On the other hand, as shown on the right-hand side, you can have MPLSPs where ingress LSRs can also be egress LSRs. So think of a bi-directional multicast tree, or again from our previous videos, think of a default MDT. Those are both sort of examples of MP to MP LSPs. Now, there is a concept that applies to both of these LSPs. This is the concept of a root, which serves the purpose of, being the root of the tree or the LSP. All of the endpoints of the LSP will signal the LSP hop by hop towards this root. So it's very important to identify what this root is. Now, for the point-to-point LSP or point-to-multipoint LSP, the root simply happens to be the ingress LSR. So each of the egress LSRs, which by the way we will call leaves from this point on, so leaves is the common terminology in MLDP, of the tree, they will signal the tree or the LSP towards the common ingress LSR, which we will also call from this point on the root. Now, we will defer the discussion of MP to MP LSP's root for right now and come back to it later in the video. So let's talk about point-to-multipoint LSP signaling first, since it happens to be the simpler one. Here's a pop quiz. How are the labels for LDP FECs distributed? I'll give you a couple of minutes here. So my email address is, no, I'm just kidding. But it is important to realize right now that LDP FEC labels are downstream distributed in an unsolicited fashion. This essentially means that a local LSR will identify the label that it wants a certain type of traffic on, and then it advertises or distributes that label to its neighbors. The neighbors will then send the traffic downstream to the advertising LSR using this label that it has provided, like earlier. Keep in mind, this is a very simplified version of the events that I'm narrating here, and in reality, things are much more complex. Number one, the IGP is intricately involved. Now, MLDP follows the same philosophy as LDP when it comes to label distribution. So this means the signaling must begin from the leaves. So let's look at an example. Leaf A and leaf B are two leaf LSRs that must signal a point-to-multipoint LSP to the root C. To begin the process, they advertise identical FECs. So identical FECs, but with unique labels to their RPF neighbor for the root, as dictated by the IGP. So same exact concept as you would have in multicast. So to keep things simple, let's assume that the middle LSR is the RPF neighbor in both cases, right? So it gets the signaling. The key difference in MLDP is that when identical FECs are received from disparate downstream neighbors, such as the case here, MLDP does not simply load share between the two paths. So what it does instead is it replicates the traffic on both the branches, as you would expect an LSP handling multicast traffic to do. So the actual contents of these MLDP FECs, they're important and they will be covered in detail shortly. But for right now, Let's suffice it to say that the FEC contains information about the ultimate destination of this particular LSP, which is the root of this point-to-multipoint LSP. And like I said previously, it is the ingress router. So the FEC in this case would contain the IP address of root C. Now, the MLDP upstream LSR, the one in the middle in our case, it reacts by adding these two interfaces as limbs of the Multicast LSP. So it utilizes the labels that have been advertised from the downstream LSRs, and it creates a label swapping operation. So the outgoing state seen right now on the slide it's not an ECMP state, but you can compare it to the OIL or the outgoing interface list in multicast routing table or a multicast state table. So it's exactly like that. You're replicating the traffic out both those interfaces using label A and label B. So next, the LSR will generate a local label, right? So for the same FEC, it'll generate a local label. It will associate it with the RPF interface and install the label switching operation. So in this case, the label switching operation for that RPF interface is label C comes in, labels A and label B go out on their respective interfaces. So now finally, this label will be advertised on the RPF interface towards the destination as identified in the FEC. So once again, this is the root. And if I repeat it enough times, then hopefully you won't have to memorize it. So this is akin to the IIF, or the incoming interface, in again the MRoute table or the multicast state table. Now, as for the data plane, the traffic on point-to-multipoint LSP, it will travel in the opposite direction from the root towards the leaves. So at every bifurcation point, the responsible LSR, happens to be the middle LSR in our case, will replicate the packets, perform the correct label swap according to its LFIB, and then help the traffic further along to the leaves. So now that we know the basics about point-to-multipoint signaling, it is time to discuss the finer details. Let's take a look at the main element here that brings this whole thing together. That is, it allows the upstream LSR to associate the MLDP signaling from various downstream LSRs together into one point-to-multipoint LSP. In the case of point-to-multipoint LSP, this element is the P2MP FEC element. All the LSRs that desire to become the leaves of this P2MP LSP must use this FEC to signal this intent to their upstream LSRs. More importantly, the content of the FEC must be identical across all the leaves. So there are two main constituents of the P2MP FEC, well really three if you want to get nitpicky, but you'll see why I stick to two and keep things simpler and clearer. So the first constituent is the root node address. Now this address can either be an IPv4 address or an IPv6 address, and that is the main reason why I said two or three constituents. You see, the first constituent identifies the address family the node belongs to. So that identifies whether you're signaling for IPv4 or IPv6. So currently we have only those two options. Now it should be obvious to most how this field should be populated. But in case if there is any doubt, yes, it contains an IPv4 or IPv6 address, most likely of the loopback that resides on the root, but it has to be associated with the root. That is the one thing. So IPv4 address associated with the root. This information in the FEC allows for two things. Number one is the proper routing of the FEC on the correct RPF interfaces all the way up to the root. So once again, just like PIM or multicast relies on the unicast routing table, MLDP is also relying on the unicast routing table to make these decisions and identify the correct interfaces. So you need to route the FEC on the correct RPF interface, and this IP helps you in doing that. Now, number two is the identification of the FEC as being unique by the LSRs. So the second field in the P2MP FEC, that is an opaque value of an arbitrary length. Now, the opaque value is called thusly because it is meaningless to most of the LSRs in the domain. In fact, the only LSRs that have to understand how to properly decode this value and read information into it and write information into it and read information out of it, they are the ingress and the egress LSRs. On the other LSRs, if you look, this value will only serve to identify identical point-to-multipoint FECs within the context of the route. What I mean is that on the middle hop LSRs, they will first identify the root of the FEC by looking at the first value, and then they will look at the opaque value that the FEC contains. So they will then proceed to compare the opaque values of all of the FECs that have been signaled for that particular route, that particular IP, and identify which ones are identical and then give them the same treatment. So what this allows for the upstream routers to do is to combine multiple branches of an LSP, as we discussed earlier. So that's our ultimate motive. Now, on the ingress and egress LSRs, this value, so on the root and the leaves, this value is not void of meaning. So they can, and in fact they do, use it to encode all sorts of information they want to pass to each other. So they're passing it transparently, well, using an opaque value, passing it transparently, hell, I don't know. But that's what they're doing, but they're passing this information to each other from the leaves to the root using this opaque value. So this information identifies what type of traffic the root should be sending on this on this multipoint LSP, and that is the traffic that the leaves expect to receive from the root over the LSP. So they must have this agreement. An example of the information encoded, you can have a unique VPN ID, for example, that identifies a particular MVPN and its multicast traffic. Another example could be a specific S-G stream. So some S-G stream in a VRF sitting behind the root that the leaves need the stream from, that can be encoded into the opaque value, and that can be sent on the MP2 .2 multipoint LSP. Finally, if it's not obvious already, it should be made explicit that the FEC is processed hop by hop, all the way from the leaves to the root to signal the LSP. And once it has made its way to the root hop by hop, then the LSP is complete. This brings us to the other type of multipoint LSP, namely the multipoint to multipoint or MP2MP LSP. We compared this earlier to PIM bidirectional BIDR or bidirectional multicast tree, and at its core, that is what it is, and that is its intended purpose, to build a bidirectional multipoint LSP. Now, one thing that we should make explicit is that so far with point-to-point LSPs and also with point-to-multipoint LSPs, everything that we have dealt with has been strictly unidirectional. So with unidirectional LSPs, as complex as the signaling is and can be, it remains unidirectional as well. But with the advent of bidirectional LSPs, we will see subtle changes in signaling. But not enough for me to not add an asterisk, as I do, to the bidirectional signaling aspect. You will see shortly why. So if I had to state a goal here, it would be to create a bidirectional LSP, but using the existing LDP signaling ethos, right? So there are some challenges to this, and we need to talk about them. One challenge lies in the way LDP works. As mentioned earlier, remember my cheesy little pop quiz? So in that, the LDP labels are downstream distributed. But downstream really is relative when it comes to a bidir LSP or bidirectional LSP. It is relative to the direction of traffic you're concentrating on at that moment. So what is upstream right now may become downstream later as the traffic pattern shifts or, an ingress become an egress. So the question is, how can we stay true to the way LDP signals FECs and still allow the upstream LSR to have control over its own label space? Because that's what it needs to do. So, and the other challenge, well, is somewhat simpler. Where does the signaling terminate? So in other words, where is the root of the MP to MP tree or MP to MP LSP, since there is no single ingress point? So the solution is twofold. Okay, so let's solve the easier problem first, because why not, right? It's simpler. So we solve this problem by picking a completely arbitrary route. And it's basically an LSR somewhere in the topology, right? Completely arbitrary. We can get into design discussions to debate whether it would, what would be the best possible position for one, but from an MLDP point of view, from the protocol's point of view, it does not matter. So as long as the LSR is part of the MPLS core, it is fine to serve as the root. So in our 4 LSR example in front of you, let's pick the middle LSR, root Z, because zombies, as the root, right? So in terms of IP multicast, we can think of this as playing the role of an RP or a rendezvous point. Now for the more complex problem. This is the bidirectional nature of signaling. Well, when it comes to this, MP to MP LSPs essentially build upon the same groundwork that was laid by P2MP LSP creation mechanisms that we just discussed. So the leaves or leafs will still start the signaling, and they still signal to the upstream LSR. And what was this? Remember, it was the RPF neighbor for the root. So simple enough and pretty much exactly the same as P2MP LSPs. But this is where we add additional mechanisms to bring that goal of bidirectional LSPs, to create bidirectional LSPs to fruition. You see, the upstream LSR is not satisfied in this case simply to receive a label and create a forwarding state and then, carry the LSP signaling onwards towards the root. In fact, we know from the FEC advertised that the intention of the leaf is to create a bidir LSP. So we will know that because the FEC is a little bit different. We will know that the intention of the leaf is to create a bidir LSP. So it knows that eventually it, i.e. the upstream LSR, will have to receive data from the leaf. In other words, it will become a downstream LSR to the leaf. So I'll repeat that again. The upstream LSR knows that eventually, if the leaf starts sending the traffic, it will have to receive that data from the leaf. And what was right now upstream all of a sudden becomes downstream. So it needs to now provide a label to that downstream LSR so it can receive that data. In order to achieve this, it basically reacts to the FEC advertisement from the leaf. And in addition to other things, so creating that forwarding space and or sort of forwarding state and all of that good stuff, it advertises its own FEC back to the leaf. This will happen for each FEC advertised. So from B and then back to it, and then from C and then back to it. That's how it is going to happen. Now this FEC contains the label that will tag the upstream data on that link. So the data going from the leaf towards root C, that is that asterisk part of the label. So once again, complete this hop by hop to the root and you have a functional bidir LSP. But this is not all. There are a few more issues that must also be resolved. So let's look at them. The major difference between point-to-multipoint and multipoint-to-multipoint LSPs is the directionality of the trees. So again, because P2MP trees were unidirectional, the loop prevention implementation, it was much simpler in the forward plane or the forwarding plane. So in fact, it has already been achieved from the creation of the P2MP LSPs without me even being specifically cognizant about it. So the mechanism I described, that already has loop prevention in it. There is no further need for loop prevention because the LSP is just going on single legs and there is no loop. Multipoint to multipoint LSPs, however, they're bidirectional. So achieving loop prevention while still optimizing the forwarding plane requires more complex mechanisms. So if, for example, say that the optimization of the traffic flow was not a concern, then what we could do is each leaf could have used a point-to-point LSP to the root, so from the leaf to the root, and then the root could replicate and distribute the flow down the point-to-multipoint tree. We could do that. That would simply not be very scalable now, would it? So at its very basic, any replicating LSR, to avoid loops or for loop prevention, it has to be keenly aware of the ingress interface at all times. Once that interface has been identified, then the traffic from that interface may be replicated safely to all of the other interfaces that are part of the LSP, but it can never be sent back on the ingress interface. That's how we prevent loops. The challenge, though, is to achieve this in the MPLS forwarding plane, in the LFIB, and while taking care of all of the other LDP, MLDP restrictions, for example, the signaling ethos. So how do we move forward? Well, one simple way is to treat the two types of FECs, the downstream FEC advertised by the leaf towards the root, differently from the upstream FEC that has been advertised as a reaction to the downstream FEC. They both result in the creation of forwarding states on the LSRs, but the state themselves and the creation mechanisms now differ, and that provides the loop prevention. So the details of the FEC, these are going to, or the FECs, it's going to be important. Since the downstream FECs create essentially a P2MP LSP to the root, they can follow the procedures we have covered earlier in the point-to-multipoint forwarding state creation. So essentially the leaf or the downstream LSR signals a downstream FEC with a downstream label to the upstream LSR, which I'm not showing here, but refer to the P2MP portion of this video, if you need to revise. The upstream LSR will simply add the interface and the label, the one that was just advertised from the leaf, to the list of other downstream interfaces and labels that the upstream traffic is swapped and replicated to. This is exactly the same thing that happens in point-to-multipoint LSP, and like I said, we've seen this a short while ago. The upstream FECs, now they need to be considered a little bit more carefully. If the replication needs to be performed as close to the leaves as possible for optimization, then the transit routers need to treat upstream FECs differently than they just now treated the downstream FECs. Time for a recap. Usually with LDP and per platform label space, a single label is attached to a FEC and then it's advertised to all of the upstream devices. So for example, if an LSR has a prefix in the FIB, say 1.1.1.1/32, it will generate a label for that prefix and advertise it to all of the LDP neighbors. In this case, with the upstream FEC, remember that upstream is downstream and vice versa. The problem with generating a single label per FEC for the transit LSRs and advertising it to all of the downstream LSRs is in creating that optimal forwarding state. Why? The reason is because each label can only have a single forwarding state, which means that each label can be associated with a single set of interfaces that the replication will happen on, the egress interfaces or the OIL, and the labels that will be used for that replication, advertised by the leaves. With the advertisement of a single label and this restriction of a single forwarding state, it makes it impossible to stop the replication from happening on the ingress interface while still allowing it to happen on all of the other interfaces, since only a single forwarding state exists. What is the solution, right? I wouldn't be talking about this if I didn't have a solution for you. So simply generate a unique label per interface and then advertise it downstream. Realize that these three labels, the navy, the saffron, the pistachio, no, I'm just kidding. So blue, orange, and green, these three labels, they advertise the same upstream FEC, but they advertise a unique label with each FEC. This part is critically important in understanding and differentiating MP2MP LSPs from both P2P LSPs and P2MP LSPs. So I will repeat. The FECs shown here, blue, orange, and green, they're identical in every single way except one. And that one is the label associated with them. Each one must carry a unique label. So this then allows for a unique forwarding state to be created for each interface because of these unique labels. What does the state contain now? So firstly, it will contain a label swap operation for the unique label, right? And in the swap and replication column, so the egress column, the LSR first adds the RPF interface towards the root. So the upstream interface as defined earlier and the label advertised by that LSR. Having taken care of getting the traffic to go upstream, it now takes care of the replication towards all of the LSRs that lie downstream. It will add all of their interfaces and the downstream labels advertised by those LSRs into the forwarding state. Yes, that last item was the downstream labels, because once the traffic has been sent upstream, the rest of the way the traffic is traveling downstream. So now it will use the downstream FECs. If that sounds confusing, rewind, listen again. Hopefully it would gel eventually. Now when the traffic comes in from the leaf LSR, using a unique label, the LSR in the middle can then replicate the traffic to the other downstream LSRs while restricting it from going back over the ingress LSR. Let's see this again. When the traffic comes in from a leaf LSR, using the unique label, the LSR in the middle can replicate the traffic to the other downstream LSRs while restricting it from going back over the ingress interface. One last time, because that is how important I think that this part is. Because of the unique label advertised, the traffic comes in with a unique label, and then it is replicated to all the other downstream LSRs while restricting it from going back on the ingress interface. And just now you have provided loop prevention. After that rather long and quite involved introduction to MPLSPs and MLDP, it is finally time to have some fun with our newfound techniques. You will realize that most of the complexity of MLDP is handled in the background, just like it was for LDP. So all the user has to do is provide the right configuration pieces. Now we will demonstrate this by showing you how to configure both the default and the data MDTs, but this time using MPLSPs instead of GRE. So guys, there's no more IP multicast in the core. This is now known as LSM or Label Switch Multicast. Well, till then, I would like to thank you for joining us, and I urge you to stay tuned for our next video. Thanks.